Welcome to the E-Pathshala lecture series in computer science. We are looking at the computer architecture course. So, this module is on cache coherence. So, the learning objectives of this module are to discuss about the problem of cache coherence in multiprocessors and to look at one of the cache coherence protocols, namely the Snoop based cache coherence protocol. So, the previous module we had an introduction to multiprocessors and we identified two major challenges associated with parallel processors. One is how much of program is going to be parallel and how much of the program is going to be sequential. We had an example in the last module which told us that even if very little of your program is going to be sequential, that itself is going to pull down your processor's performance, multiprocessor performance. So, which means that we will have to try and write parallel programs as far as possible, because when anyway we have an underlying hardware which can work in parallel. So, if you do not really exploit the hardware, the parallelization that is provided by the hardware, then we may not reap the benefits of your architecture. The second issue is of course the communication latency. Communication latency, we know that even if you have very little communication latency, that is going to have a major effect on the multiprocessor performance. So, the solution to handling your communication latency is, can we look at caching the data in multiple processes. So, instead of having the data in one place and all of them trying to get the data from there, and which will lead to communication latency, can we look at caching the data in multiple processes. So, as each processor wants a data that it is going to commonly use, can that data be cached in the processor's respective caches. So, you know that caches will serve to increase your bandwidth versus your memory or the bus speed. It will try to reduce your latency of access. It is going to be valuable for both private data as well as shared data. But the moment you bring in caches in a multiprocessor system, you also have the problem of what is called the cache coherence and the cache consistency problem. Remember, in a memory hierarchy itself, when we looked at multiple levels of memory and we had one block of the data being transferred say from the main memory to cache, and the cache got modified, then we had a consistency problem there. So, we either looked at a write through protocol or a write back protocol to ensure that both the copies have consistent information. So, that was in a uniprocessor architecture. Now, the same thing can be extended to a multiprocessor architecture. So, you have multiple processors, each one of them is going to cache the same data depending upon their requirement. So, which will lead to different caches having different information about the same block, which is definitely a problem. So, this is an example to tell you what is the problem of cache coherence. So, basically the processors may see different values through their caches. Say for example, when let us assume that processor A reads a value of x and the value is 1. So, the processor's A's cache stores this information. Subsequently, processor B also reads the same data. So, it gets the same data from memory and it caches it. But subsequently, when processor A modifies the data and stores a 0 there, then B has also cached the data and it has stored a 1. So, there is an inconsistency of data of the same data that has been shared between the multiple processors. So, that gives rise to what is called the cache coherence problem. So, coherence, what do you mean by cache coherence is, all reads by any processor must return the most recently written value, and writes to the same location by any two processors have to be seen in the same order of writes by all processors. And what you mean the consistency here is, when this value is to be read, when a written value will be returned by a read, so that you get the correct information. So, if a processor writes location A followed by location B, any processor that sees the new value of B must also see the new value of A. So, if you look at the coherence problem and the consistency problem, coherence is more of what data is being read by a processor when it is modified by some other processor. Processor modifies it, the same processor reading it or a different processor reading it must get the modified information. That is a coherent problem, what value. Consistency is when if a processor reads the value, will it get the correct data. So, that is a consistency problem. So, informally what coherency means is any read must return the most recent write. So, obviously it is too strict and too difficult to implement. So, we will look at a more generic or a formal definition. This is a better way of stating it. Any write must eventually be seen by a read, and all writes should be seen in the proper order. That is your serialization problem. So, we have two rules to ensure this. So, if processor P writes X and P1 reads it, P's write will be seen by P1 if the read and write are sufficiently far apart, and writes to a single location are serialized, that is they are seen in one order, and the latest write will be seen as the last one. Otherwise, what will happen is we could see writes in an illogical order. You could see the older value after a newer value, which will definitely is not acceptable. So, to enforce coherence, before we go into the coherence problem, the basic problem of coherence comes up because you have the support for migration and replication. So, caches provide migration and replication, allow for migration and replication. You allow for movement of data from main memory to one cache and from main memory to another cache also. So, that is called the migration of data, and you allow replication of data, which means multiple copies of the same data can be available in different caches. And because you support migration and replication of data, you will definitely have the cache coherence problem, and we will have to look at ways of handling the cache coherence problem. Now, there are two basic protocols which are used for enforcing the cache coherence. One is the directory based protocol, the other one is the Snoop based protocol. In the case of a directory based protocol, the status of all the cache blocks is kept in one place, which is called the directory, whereas in the case of a Snoop based protocol, each core tracks sharing status of each block. So, each cache controller has information about its own cache, and a general snooping happens on the bus. So, everybody looks at what is transmitted on the bus by a snooping activity that try to enforce the coherence. So, potential hardware coherency solutions, as I told you, one is a snooping solution. In the case of a snooping solution, we make use of the bus is the most common interconnection. So, you have a Snoopy bus, you send all requests for data to all processors. The processors snoop to see if they have a copy, and accordingly they respond, and this requires a broadcast since caching information is at processors, and it works well with a bus, which is a natural broadcast medium. And this is basically very useful. It dominates when you go in for small scale machines, because it has a scalability problem when you look at larger machines. On the other hand, directory based schemes keep track of what is being shared in one centralized place, at least logically. So, you have a distributed memory. In a case of a distributed memory, you can distribute the directory for scalability, and you can send point to point requests to processors via the network. So, this method definitely scales better than your Snoop based approaches. This method actually existed even before the Snoop based schemes. So, if you look at the Snoop coherence protocol, you can either look at a write invalidate approach, or you can look at a write broadcast approach. So, if you are looking at a write invalidate approach, suppose a processor holds a copy of the data, it has read the data, that data has also been read by some other cache of a processor, and suppose if one processor wants to perform a write on this data. So, when the processor performs a write on this data, the other data is going to be something else. So, you have a coherence problem. So, one way of handling this is you invalidate the data. When a processor performs a write on one data, it invalidates all other copies, and it uses the bus to serialize these activities. That is the write invalidate approach, which means because you are using the bus to serialize, the write cannot complete until the bus access is obtained. So, this is an example that shows how invalidates can happen. The second one is a write update process, which means just like a write through protocol, whenever one processor is modifying a cache location, it just broadcasts this information to everybody, and everybody modifies this information. So, it is similar to our write through approach. So, you basically can use one of these approaches. One is a write invalidate approach and the other one is a write update or a write broadcast approach. So, if you look at the write invalidate protocol, you basically have multiple readers, but you can have only a single writer. So, a write to a shared data will have to be done by sending an invalidate to all caches, which snoop the activity going on in the bus and they will invalidate all their copies. And if you have a read happening, if it is a write through, you know the memory is always up to date. If it is a write back, then you will have to snoop in the caches to find out the most recent copy. Because if you use a write through protocol, anyway it is going to be updated in memory. So, you can always read it in memory. Whereas, if you use a write back, an invalidate protocol, it basically does a write back because the copies have been invalidated here. So, you, the one that is when somebody requests for a data, the recent data will have to be written given back to that data, which is again done by means of snooping. Write update or write broadcast protocol is typically similar to your write through protocol. So, it writes to shared data and it broadcasts on the bus. So, all the process snoop these activities and they update whatever copies they have. And if there is a read miss, the memory is always up to date, and of course, you will have to do a write serialization, which is basically a bus serialization request. Bus is a single point of arbitration. So, if you look at the comparison between these two protocols, write invalidate versus write broadcast, multiple writes to the same word or word within a block, there is only one invalidate happening if you are looking at a write invalidate approach. An invalidate basically uses spatial locality because there is only one transaction per block, and the broadcast has lower latency between the read and write. Whereas, if you look at the invalidation protocol, you have other benefits associated with the invalidation protocol. Now, what we will assume for our discussion here is an invalidation protocol, a write invalidation protocol with the write back cache. To elaborate on the Snoop based protocol, let us assume that the cache is available in 3 states. So, the block of memory can either be shared by multiple caches. So, the data has been shared by multiple caches. So, the memory is available in a shared state, or it can be exclusively available only in one cache because it has been modified. So, it is dirty there, or it may not be cached in any of the caches, it is in an invalid state. Similarly, if you look at the cache block in one state, the cache block can be in a shared state, which means it has been read, or it can be in an exclusive state, which means it has been modified there in that processor, or it can be invalid because that block contains no data. So, we are looking at a Snoop based protocol where multiple processors can cache in the information and all the coherence happens through the common bus. Everybody snoops on the activity that goes on in the bus. So, read misses will cause all caches to snoop on the bus, and whoever has to respond to this read miss will respond with the data that they have. Writes to clean data are treated as misses. So, this is the Snoopy coherence protocol that we have looked at. So, you can have different types of activities that are happening here. The two basic activities that you can look at is the processor can generate a read request or the processor can generate a write request to your cache controller. So, when by means of either a load instruction or a store instruction. So, depending on what request the processor generates, a read or a write request, and depending upon the status of the cache block there. So, the cache block can be a miss or a hit in the cache controller. So, depending on that you have different activities that can take place, that is one thing. And even if the processor is the cache block is available there, it can be available in different states. It can be available in a shared state or it can be available in a modified state. So, depending on all these possibilities, this table lists the various possibilities that can happen and the various activities that can happen for your Snoop based protocol. Say for example, the request, so you remember that your cache controller is in the middle, the processor puts in a read or write request here and you have the bus on the other end which is trying to connect up all the various caches. So, when you look at a read hit by the processor, the block itself can be available in the shared state or a modified state, which is just a normal hit, you just transfer data. If it is a read miss by the processor, which means the data is not available. So, if the cache block is available in an invalid state, then you will just have to place the read miss on the bus and the data that is available in memory will be transferred to the processor. And if it is a read miss by the processor and the cache block is available in a shared state, it basically means that some other processor has already read in the data. So, it is available in a shared state. And one assumption that we make is if a block is available, a cache block is available in a shared state, we assume that the main memory has a copy of the block. So, if your data is available in the shared state, you know that the data is available in your memory, updated data is available. So, it is just similar to a replacement miss, it is only an address conflict miss, you place the read miss on the bus and the memory will respond with the data. On the other hand, if it is a read miss and some other processor has cached this cache block already and it is available in a modified state. So, one processor has already read in this data and written something onto it, it is available in a dirty state and some other processor is requesting for the data. This means that you will have to write back the block, because the memory will not have a copy of the block. So, this processor is reading it. So, you definitely have to respond, the one that is holding the data in the modified state will have to respond. So, it will have to respond to the conflict miss, it will have to write back the block and then place the read miss on the bus and satisfy the requirement. So, that is what happens when you look at a data that has been modified. And also the status of the cache block, originally it will be modified in that cache controller. So, now from modified, because somebody else has already read it, it will have to change from modified to shared. Similarly, when you are looking at the write request, if it is a write hit and the processor is already holding it in the modified state, then it is a normal hit, you can go ahead and write the data in the local cache. If it is a write hit and the processor is holding it in a shared state, modified state means it already has ownership of the data, it goes and writes the data, there is nothing to be done. But if the data is available in a shared state, it means it is only holding it in a shared state and now it wants to write data. So, it becomes a coherence type of cache action, because you will have to find out who else is holding it in the shared state and invalidate all their data. So, it sends this address which will go on the bus and everybody holding the data in a shared state will invalidate the data and then it will perform this operation of write. Similarly, if it is a write miss and the processor the cache block is available in an invalid state, it is a normal write miss where you will get the data from your main memory. And if it is a write miss and the block is available in a shared state somewhere, it means it is an address conflict miss, you will have to place the write miss on the bus. And if it is a write miss and the block is held in a modified state somewhere, the other processor which is holding the block in the modified state will have to write back the block, then place the write miss on the bus. And similarly, when you are looking at the other side of the activities happening on the bus, these are the activities that happen on the processor end. If you look at the activities that happen on the bus end, when you have a read miss coming in on the bus and the status of the address cache block is shared, you do not have to perform any action because the memory is going to service your request. If there is a read miss coming in on the bus and the block is available in the modified state, it becomes a coherence. So, somebody is trying to take the data in a shared state and the data is already available in the modified state. So, you will have to place the cache block on the bus and change the status from modified to shared. Similarly, if there is an invalidate request that is put in on the bus and the cache block is available in the shared state, so you are trying to do a write operation on the cache block which has been shared, so you will have to invalidate the block. Similarly, if there is a write miss on a shared block that is happening, that is again a coherence miss, and you are trying to write a shared block, so you will have to invalidate the cache block. So, the last case is you have a write miss coming on the bus for the address cache block being available in the modified state. This is again a coherence miss because the block is available already in the modified state, but there is a write miss coming in. So, somebody else wants to perform a write operation here. So, the other data will have to be anyway invalidated and this person has to get the ownership of the data. So, there is an attempt to write a block that is exclusive somewhere else. So, you will have to write back the cache block and make its state invalid in the local cache. So, these are the various activities that happen in your Snoop based coherence protocol, and this is a state diagram showing the same activities here. So, you have your cache controller cache block available in an invalid state or a shared state or a exclusive state. So, depending upon what state the cache block is in the various cache controllers, and depending on what is the request of the processor, either a read request or write request put in by the processor, it may either be a read hit or a write hit, or it can be a read miss or a write miss. So, depending on that and depending upon the address that is transmitted on the bus, you have the various caches responding to it. So, this is your state machine, one state machine. This is from the cache blocks point of view, and this is a combined state machine. So, the state machines give you the same information as we discussed in the table. So, what you have to remember in the case of a Snoop based cache coherence protocol is that all the cache controllers have information about their own caches, and you have a common bus connecting all the cache controllers. So, any activity or any request that the processor puts into the cache controller, that request is transmitted to the bus. Say for example, if it is a read miss, the read miss is transmitted on the bus, which is snooped by all the cache controllers. So, the other cache controllers are looking at this address, they know that there is a read miss for this request. So, depending on whether they have this data or not, and depending on the status of this cache block, they will respond to it. Suppose say for example, if one cache controller already has it in a shared state, he knows that he is only holding it in a shared state. So, the memory anyway will have a copy of it. So, he will not bother to respond. But suppose if a cache controller is holding it in a modified state, he will know that he is the only one holding the data. So, he is responsible for giving back the data. So, he will write back the data onto memory and pass on the data to the requesting processor, and at the same time he will change his status from modified to shared. So, all these activities happen on the bus. So, the state diagrams basically give you the same information as that of the table that we discussed. So, this is an example to show what happens. There is a request, initially you have a request given. So, what will happen to the various reads and writes happening on the in the Snoop based protocol. The only thing that you will have to assume here is A1 and A2 map to the same cache block, but A1 is not equal to A2. So, what will happen when there is an initial request put in? If it is a read request that you are looking at, so you can just take it from memory and the read request is satisfied. But if it is a write request that you are looking at, then you will have to remember that a write invalidate has to be sent to all the cache controllers that are holding it. So, they will have to be first of all invalidated, and only then you will have to modify the data. Just remember those basic concepts, and you have you can go through this example. So, now looking at the implementation complications, having looked at the basic protocol, which is an MSI protocol. This is called the MSI protocol. M stands for modified, S stands for shared, and I stands for invalid. And in a normal cache, you know the cache anyway has a valid bit available. So, the valid or invalidity of the block can be maintained by means of the valid bit, and the modified bit you anyway know that there is a dirty bit which is already available. So, by setting the dirty bit to 1, you can indicate whether the cache has been written or not. So, that is how your dirty bit or modified bit is maintained. You may have to have an extra bit which indicates whether the cache is available in the shared state or not. That is the only extra addition that you will have to provide. So, having looked at the Snoop based protocol, now we look at what are the implementation complications associated with your Snoop based protocol. One is write races. You cannot update the cache until the bus is obtained. Otherwise, what will happen is another processor may get the bus first and then will write the same cache block, and you will have two different data. So, this basically you have a two-step process here. You will have to first of all arbitrate for the bus, play and then place miss on the bus and complete the operation. And if miss occurs to block while waiting for the bus, you will have to handle bus by invalidating whatever is block is required and then restarting. So, we are looking at a split, you may look at a split transaction bus here. where the bus transaction is not atomic, it may have multiple outstanding transactions for a block, and multiple misses can be interleaved, allowing two caches to grab block in the exclusive state. You must obviously track and prevent multiple misses for one block. So that is one problem, and you also should have support for interventions and invalidations. So the basic two problems are, you have multiple processors must be on the bus, they are trying to have access to both addresses and data. So which means you may have to add a few commands to perform coherency in addition to the read and write, and processors continuously snoop on the address bus. So if address matches the tag, you either have to invalidate the block or you will have to update the block depending on the request that is coming in on the block. And since every bus transaction checks the cache tags, this could basically interfere with the CPU, because you know that you to the cache controller, one end the CPU is putting in a request and the cache controller will have to put in a request to the buses on the other end. So when the bus transaction is happening and a tag checking is happening, the CPU might have to be delayed. So you have an interference there, and you obviously cannot have the CPU getting delayed. So in order to avoid that, there are two solutions. One solution is duplicate the set of tags, so that the processor uses one set of tags and the bus uses the other bus uses the other set of tags. In case there is any change happening, then you will have to do the updates. That is the first solution. The second solution is try to look at an inclusive cache. But if you look at an inclusive cache, obviously the problem is it will have an effect on the block size, and it will have an associativity effect on your associativity. So if you look at the implementation again, the bus serializes writes, getting the bus to ensure that no one else can perform the memory operation. On a miss in a write back cache, it may have the desired copy and it is dirty, so it must reply, and you may have to add an extra state bit to cache to determine shared or not, which is what I mentioned earlier. So you may apart from the valid bit that you have and the dirty bit, you may have to add a shared bit. Now this is the basic protocol, the MSI protocol that we looked at. Can we add other states to the MSI protocol so that you are able to bring in some optimizations to the cache coherence protocol? One possibility is adding a fourth state, which is called a messy protocol. Now why do we have to add a fourth state is basically summing up the complications associated with your basic MSI protocol. Operations are not atomic, though we know that they will have to be done in an atomic fashion. You know, the operations are basically not atomic. For example, the detecting bus, acquiring the bus and receiving a response, all of them may not be done atomically, which means this will create possibility of deadlocks and races. So one solution is the processor that sends invalidate can hold the bus until other process receive the invalidate. So extensions to your Snoop coherence protocol, all these complications will have to be handled while you are implementing the Snoop coherence protocol. Now in order to optimize some of these this protocol, you can look at extensions to the Snoop coherence protocol. One extension is you can try to add a new state, which is called an E state. We looked at earlier, we looked at an MSI protocol. This is a messy protocol where you are trying to add a new state, which is called the exclusive state. This exclusive state indicates a clean block in only one cache. Earlier we had a modified, we had a shared, and we had an invalid state. Now we are adding a new state, which is called the E state, which is called the exclusive state. Exclusive means that this is the first cache controller to read the block and it has still not modified it. So it is holding the block in a clean state. The advantage of using this is, suppose if this cache controller wants to do a further write on this block, it knows that it is holding the block in the exclusive state. So no other cache controllers have actually cached this block. So there is no need for sending invalidate signals to the other blocks. So the optimization that you do here is the removal of the unnecessary invalidates that you will have to send when you are doing a write operation. So that is one extension that you can do to the MSI protocol. The other extension that you can do to your MSI protocol is messy with a forward F, that is your messy F protocol, which is used in your Intel i7 processors. Now, apart from the 4 states that you have as messy, modified, exclusive, shared and invalid, you also add a 5th state which is called the forward state. Now, the forward state basically what it tries to do is, you know that when the cache block is available in a shared state and there is a request for a read operation on by any other processor which wants to share this block also, you know either the main memory can respond with it. Normally we assume that the main memory will respond to it, but because the main memory has an updated copy. But what happens is, if you are going to take the data from main memory, it is going to take a long time. So, you can also have any of the other cache controllers responding with the data, because they anyway have the data. So, that is what is normally done. But again you have a problem, if multiple cache controllers are caching the same information, who is going to respond to this request? Otherwise, there is going to be a collision between the multiple transfers. So, if you include a forward state, it gives the status of forwarding authority to a particular cache. So, when there is a request coming in for this block on the bus, the cache controller which holds this block in the F state is the one which will have to respond to this request. So, that is what is meant by forward. But you again have a problem here. So, somebody is given the designation of forward, and suppose that cache block is eliminated from the cache by a replacement policy, then who is going to respond with the data? Again you will end up with a similar problem. So, in order to avoid that, normally what is done is, the forward state is always transferred to the most recent processor which reads in this cache block, because you know, because this processor has only read in the data most recently. So, that processor is not going to eliminate the data too soon. So, this forward state is passed on to the processor which reads in the data latest. So, that is how you can do some optimizations. The last optimization that we are looking at is a MOSI protocol, which is used in your AMD Aptron processor. The MOSI brings in what is called an O state, which is an ownership state. So, basically what happens here is, normally when you have a data, a dirty data, you have a block that has been written and somebody else shares this data, you know that when it changes from your exclusive state to the, or the modified state to the shared state, this data is being written back to main memory, so that the main memory has an updated copy. But here what we do is, even if the status changes from modified to shared, we bring in a new status called the owned data, in that is to avoid the write that will have to happen to your main memory. So, the owned cache is containing the dirty data. It may be shared by other processors. So, the other processors have read in this data again. So, they will hold it in the shared state, but there is only one cache block which holds it in the owned state, which means that this cache block had modified it. So, it has a copy of it, it only has a copy of it. The main memory does not have an updated copy, but other processors have read it for sharing purposes. So, that is your MOSI protocol. So, you can have different types of these protocols. By just adding more states, you are making the state controller more complicated, but you are trying to bring in optimizations to your coherence protocol. So, extensions to your coherence protocol, you can try to look at the shared memory bus and snooping bandwidth, because they are a problem for scaling. You can try to duplicate the tags, as I already mentioned. You can look at a combination of directory based protocols and Snoop based protocols, and AMD Aptron basically uses this type of architecture, a combination of these two protocols. This is the example that we have for cache Snoop based coherence protocol. We'll just go through this example based on the basics that we discussed in this module. So, to summarize, we have had a paradigm shift from simple processors to simple processors, in the sense that you have a uniprocessor system to multi-core architectures due to various reasons, and there has been a need for parallel architectures, and you need to address the problem associated with high communication latency of parallel processors. So, for that you will have to use caches, but when we use caches, we have the problem of cache coherence. So, how do we handle the cache coherence problem? You can try to look at two different protocols. what we looked at here is the Snoopy protocol, and of course, you have different implementation issues associated with the Snoopy protocol. So, we looked at all the implementation issues, and we also looked at the drawbacks to this protocol. We also looked at how you can extend this protocol further by bringing in new states, which will try to bring in some optimizations under certain circumstances. So, these are the references. Thank you.